In my example, the problem was this too. I should have used a number which is smaller than 1 here in this example. So let us do that. Say instead of 2, let's make it 1 over 2. So it's less than 1. Now if it is 1/2 instead of 2, then this would be 1 over 4. This would be 1. This would be 1. And then, all right. Then we would have 1 over 4 here. And c square, we still assume it is a real number. C square is 1 minus 1 over 4, which is 3 over 4. Then C could be plus or minus, but we take the plus sign, square root of 3 over 4. So this function then, g equals 1/2 f1 plus square root of 3 over 4 times f2 is not normalized, which means this integral with the choice for c2 square root of 3 over 4 will be equal to 1. Normalization integral. Okay. Let's go back to operator concept. We have already discussed the fact that in general 2 operators do not commute. However, there are some simple cases in which we can tell that the 2 operators do commute. And now I'm going to outline these simple cases. Operators commute with each other. One case is an operator A commutes with itself and all of its powers, or any expression containing its powers. So A first power, second power, third power, and so on, any power. A commutes with all of these operators. Also, these are the powers. Any expression, say C1 times A plus C2 times A square plus C3 times A cube. If you construct a new operator from A square, A cube in this way, where C1, C2, and C3 are constants, and call it B, A will also commute with such an expression, which contains the powers of A. So this is one case. Second case is A and B depend on different independent variables. If A depends on, for example, X variable, but B depends on Y variable, these two variables are independent, then A and B automatically commute. We had given an example for that. Let's take this operator, first derivative with respect to X, and another operator which is also first derivative, but this time first derivative with respect to Y. X and Y are independent variables. These two operators always commute. Another important case is the following. Later we are going to discuss electrons. Electrons have spin property. And as a result, there are spin variables. Now, spin variables are independent from space variables. Space variables describe the location of the particle in space, whereas spin variables are related with the spinning of the particle. And these two types of variables are independent. As a result, if operator A contains just space variables, but operator B contains only spin variables, then A and B, such A and B, will always commute. Now, finding commuting operators, or realizing that two operators commute with each other, is quite important. Why? Because of the following property. When two operators commute, then they have the same set. They have the same set of eigenfunctions. Let us give symbols A operator and B operator. What does this mean? This means that suppose we have a function f, and we are told that this f is an eigenfunction of A with the eigenvalue k. Then the same function f is also an eigenfunction of B, but the constant which multiplies f here, of course, could be different from the first constant. So let us say this is B. The same functions for both operators A and B, because A and B commute. However, the eigenvalues are different. This is the importance of commuting operators. Now let us have an example using A and B. This B here. Now we have told you that because this B is an expression made up from powers of A. Such an expression for any value for C1, C2, C3 will commute with A. Therefore, A and this B should have the same set of eigenfunctions. So it is this one for B. Using this property for A, we can simplify the result of applying B to the function, the same function f. Definition of B is C1 times A plus C2 times A squared plus C3 times A cube acting on f. Now we expand this expression and apply the known result. C1 times A f plus C2 times A square f plus C3 times A cube f. Now, but K is a constant. Our operators, quantum mechanical operators, do not do anything to constants, which means constants can always be taken out. So this is K times AF. But we can replace AF once again with K times F, always using this expression. So the final result is, this is K squared times F, isn't it? So this expression here is K squared times F. Similarly, when you do it with this, what do you think we are going to obtain after simplifying it? A cube acting on F will give us K cube. Now, all terms contain F. So we factorize F. What are the terms I should write? C1 times K plus C2 times K squared plus C3 times K cube. So now compare this part. With the final simplified expression. Operator function equals constant times function. Therefore, is the same function f also an eigenfunction of B? Yes. What is the eigenvalue of B? This expression inside parentheses. You see, all of these are constants. C1 times K plus C2 times K squared plus C3 times K cube is the eigenvalue for the B operator. Please note once again that the function f is the same for both A and B, but eigenvalues are different. Now we came to an important point. We are going to discuss how to write quantum mechanical operators explicitly. This is something we need because we have to make things explicit when we try to solve problems. Quantum mechanical operators are obtained starting with classical expressions. Classical expressions are expressions, in fact, they are scalar expressions, classical expressions. These expressions are available from the work before quantum mechanics have emerged. we are going to discuss the rules for writing explicit expressions for quantum mechanical operators. Now, to do that, let us start with some concepts. Concept of observable. Any property that can be experimentally observed about a system is called an observable. If we say it from the opposite sense, if something cannot be experimentally observed in the laboratory, then that thing does not exist. To call it observable, it must be experimentally detected. Now, quantum mechanical expressions for the operators are obtained from classical expressions for the observables. Now, we will use this symbol T for the kinetic energy. Symbol for kinetic energy. It is a standard symbol, all right. In quantum-related textbooks, you do not see, say, this symbol, kinetic energy, but you see the capital T symbol. Whenever you see the T symbol, you should assume that we are talking about kinetic energy. Similarly, the standard symbol for potential energy is V. For any system we study, there is a potential energy function, V. V depends on the variables which are contained in our system. Potential energy function for any system is classically known. Therefore, this means that whatever system you take and study, the potential energy function of that system is classically known. In quantum theory, the classical expression for the potential energy function appears directly without any change. The same expression, the classical expression V, occurs in quantum theory. The different points or features of quantum theory is in the expression that we use for kinetic energy. Now, at the beginning, I am going to discuss the classical expressions, and then after that, I'm going to tell you the rule about how to convert the classical expression into quantum form. All right. Now, let us start with some idea, classically known quantities. This is the standard definition of linear momentum, isn't it? Left side is linear momentum, right side is using the velocity vector. And m is the mass of the particle. Of course, if the particle is moving in 3 dimensions, this p is a vector with components. Similarly, velocity is a vector with components. Now, the expression for kinetic energy for a single particle can be written either this way, 1/2 mv square, using the speed of the particle, all right? Or we may write the same expression using linear momentum, because p square is equal to m square times v square, isn't it? If we eliminate this v square using that expression, we will obtain this. The upper expression is using speed of the particle, and the lower expression is using the linear momentum of the particle. Okay? Now, when we want to obtain quantum expressions from classically known expressions, such as this one, we always use linear momentum, not the speed. So this is our expression for kinetic energy in quantum theory. This is using linear momentum. Okay. Of course, this symbol p square, classically it is the square of magnitude of linear momentum, right? But if you know the components, here are the components. P square means px square plus py square plus pz square. If this particle is moving in three-dimensional space. The classical expressions should be written using Cartesian type variables, not any other variables such as polar variables, but Cartesian type variables, because the rule for converting a classical expression to quantum expression works only if you use Cartesian type variables. After you obtain the operators, then you may want to change the type of variables. But before doing that, you should express everything using Cartesian type variables, and then I'm going to give you the rule, obtain the quantum expression, and then proceed. The rule for obtaining quantum expressions from classical expressions contain only the kinetic energy part. In fact, the linear momentum. Only that part will become different from classical expression. Before giving the rule, this expression kinetic energy plus potential energy. This is, of course, classically the total energy, isn't it? Kinetic energy plus potential energy is the total energy. Now, when you write such an expression, kinetic plus potential energy, in which if the kinetic energy is written using the linear momentum instead of speed, not this form, but this form, all right? Then this is given a special symbol. It is called Hamiltonian of the system. I am remarking here, must be the qth component of the linear momentum in the classical expression becomes an operator, and this operator is minus I times h bar times the first derivative with respect to the qth variable. Here, q may be either x or y or z. In other words, in this expression, this term px square becomes px operator square. And these are partial derivatives with respect to the independent variables. These are the expressions for the x, y, z components of the linear momentum of a single particle. Now, to write the kinetic energy expressions, we need p square, which is px square plus py square plus pz square. So let us write explicit quantum expressions for px square. Px square is the square of this operator. Now we can simplify this a little bit. These are constants, minus I times h bar. This is also minus I times h bar. Minus I times minus I gives us, simplify, 1 or minus 1. Signs are same. Minus times minus is plus. I times I, minus 1. So there is an overall minus h bar square. And it is this. What does this operator mean? You see first partial derivative with respect to x and also first partial derivative with respect to x. But you should regard them as like this. After applying a to f, then you apply it. So what does it mean? After taking first derivative with respect to x, now you take the first derivative with respect to x of the result. The result was this. After applying the first partial derivative. Now you apply partial derivative to this expression, you get the second derivative. So this is the symbol for second derivative, which means the operator, which corresponds to square of px, is just minus h bar square times second derivative with respect to x. Similar expressions will be obtained for py square. The only difference is instead of x, you will have y, and for pz. Therefore, our quantum mechanical kinetic energy operator is not this expression. But T will become operator because P becomes operator. So I put a hat, kinetic energy operator. You see, it looks exactly similar to this expression, isn't it? But what is the difference? Here P is a scalar, T is also a scalar, but here in the quantum expression, this is an operator, and because it is an operator, T becomes operator. Now, the expression for P square is Px square plus Py operator square plus Pz operator square. Now, what is Px square operator? It is this expression, minus h bar square times second derivative with respect to x. Similarly for Py, similarly for Pz, which means the explicit expression for kinetic energy operator of a single particle is there is a minus h bar square divided by 2 times m. These are constants. And then we have sum of partial derivatives. Sum of partial derivatives. The expression inside the parentheses is called Laplacian. And there is another symbol that we learned in the CHEM 257 course. This symbol is used, del square, to mean sum of second derivatives. So this is our kinetic energy operator. Then this is the definition of Hamiltonian, classical definition. Kinetic energy plus potential energy. The quantum expression is potential energy, you do not change. It is the same expression as in classical theory. What changes? Kinetic energy becomes operator. Like here, you see these are operators here. Now, because kinetic energy becomes operator, the Hamiltonian becomes operator because of this term. Operator means it's something different from a scalar, all right? You have sum of 2 terms here. One of them is an operator, therefore the result cannot be a scalar. It must be something different. Yes. Kural öyle. Yani şimdi yani buradaki argümanlar şöyledir. Bir varsayımda bulunursunuz. Ondan sonra o varsayımları sonucuna bakarsınız. Mesela buradaki varsayım şu kinetik enerji ifadesini öyle kullanalım. Potansiyel enerji ifadesini hiç değiştirmeyelim, aynısını kullanalım. Ondan sonra ne yapıyoruz? Schrödinger denklemini çözüyoruz. Oradan bir takım sonuçlar buluyoruz. Ondan sonra çok önemli, deneyle karşılaştırıyoruz. eğer bu varsayımlarla Schrödinger denklemini çözüp orada bir takım rakamlar bulup o rakamların deneyle çakıştığını, örtüştüğünü görüyorsak seviniyoruz. Diyoruz ki bizim en baştaki varsayımımız demek ki tutarlı, tutuyor. Tabii tek bir sistem yetmez. Pek çok sistem üzerine deneme yapıyorsunuz. Her defasında deneye başvuruyorsun, deneysel sonuçlara. Onlar örtüşüyorsa diyorsunuz bu model, bu teori çalışıyor. Bunu böyle mesela milyonlarca kez farklı sistemleri tekrarlayıp belki milyonlar bırak yani 10 milyonlar, 100 milyonlarca farklı sisteme uygulayıp hep her defasında deneyle örtüştüğünü görüyorsanız artık kafanızda kuşku kalmıyor. Diyorsunuz ki benim şu varsayımlarım geçerli varsayımlar. Şimdi deneyle bir çelişki olmuş olsaydı derhal çöpe giderdi bu şey. Bir tane bak 10 milyon da doğru olsun, bir tanesinde tutmasın. Yani bir çelişki olsun, o bile çöpe götürür teoriyi. Potential energy expression, the actual expression is not changed when we use it in quantum theory. It is the same expression as in classical theory. The only difference is in the kinetic energy part. Let us look at this example to move a little bit away from hard theoretical concepts. Show that the set of functions fk, which is equal to e to the I times k times x. All right. Here, k is a constant. I is the complex number, square root of -1. X is the variable. X is a real variable, of course, ranging from -infinity to +infinity. We have taken this function in another example. There, we had shown that the constant k must be a real number. Do you remember that? K has to be real. We have used the conditions that acceptable functions must satisfy to prove that k must be real. So we can write k is a real number. Now, I have written k as a subscript because if we use a different value for k in this expression, we are going to obtain a different function. So for each, imagine k is changing from some value to another value. For each different k value, you have a different function here. That's what I mean by f sub k. Now, question mark, I have put question mark. What does it mean? Is this expression true or not? There are just two answers, either yes or no. If the answer is yes, the expression is true. In that case, this function f will be an eigenfunction of px. And what will be the eigenvalue? This scalar symbol, p. Otherwise, if the answer to this expression is no, which means that after you apply px on f, you do not get something, the original f multiplied with a constant. In that case, we are going to say f is not an eigenfunction of px. So, now we simplify this expression. What is the expression for px? Minus I times h bar, partial first derivative with respect to x. So this is our expression. Now what is the partial derivative of this exponential with respect to x? Come on, exponential. Here is x variable and first derivative of it. Constant, which multiplies x times the same function. Simplify this. Here the constants can be simplified. Minus I times I. What is it? Plus 1 or minus 1? Biri eksi öbürü artı. Plus 1. Then h bar times k times the function. All right. Now you compare this. You compare this result with this one. After applying the op px on f, did you obtain the same function? By definition, this is f. After applying px to function f, did you obtain f times a constant? Yes. Therefore, what is the answer to this question? Yes or no? Yes. Then you ask, what is p? The eigenvalue. Look at here, what is p? P is the constant which multiplies the function. Which constant is multiplying this f? H bar times k. Therefore, p is h bar times k. Please remember, this course is using mathematical terminology, but our subject is not mathematics. Therefore, and because of that, every symbol here has a unit. If we say this is a momentum, linear momentum, it must have a unit. That unit you may infer from here. What is the unit of linear momentum? Mass. Use the SI units. What is the SI unit for mass? Kilogram. Multiplied by, what is the SI unit for velocity or speed? Meter per second. This is the kilogram times meter per second is the SI unit for linear momentum. So this operator will also have that same unit, and P will also have that unit. In equations, units must be consistent. If you have some set of units on the left side, on the right side, the same units must be present. So this P has a unit. What do you think the unit is in SI? It will be momentum unit, kilogram times meter per second. Now, K will have a unit. Look at here. K times X. What is X? Distance. What is the SI unit for distance? Meter. K times X, because it occurs in the exponential. K times X cannot have any unit. No unit. Which means K itself should have, if this is meters, this would be 1 over meter. Meter to minus 1. It must have that unit. Now, h bar is h divided by 2 pi. What is the unit of h? Joule times second. Unit for K is 1 over meters. Joule times second divided by meters. If you analyze it, you must obtain this. So keep all these things in mind. Every symbol has a unit in our discussion because we are studying real systems. Atoms or molecules are real particles, and their properties certainly will have units. All right, we stop here.